Alright, so here we are with the 5-3 notes. Our 5-3 notes are on medians and altitudes. So we're going to construct some medians and altitudes of a triangle and see what happens there. So of course we'll be doing medians, and it turns out that medians, once you construct all of them, will actually lead to a point of concurrency called a centroid. Altitudes will then all meet to make something called an orthocenter. So we will have that. So here we are with a median of a triangle. A lot of people confuse this with an angle bisector. Okay, what happens is the angle bisector tends to come from the vertex as well, but of course it ends with two pieces that angles are the same. Now, of course, can a median be an angle bisector? Sure, but it will not always be, and so therefore we can't just assume. So if we take a look, what we're actually getting is two pieces of that opposite side of this vertex, connecting it to that median. So a median of a triangle is a segment whose endpoints are the vertex of the triangle, in this case C, and the midpoint of the opposite side, which would be D. Every triangle has three medians, and the medians can be concurrent, which means that they would meet at a point. So if I drew this one accurately, not that that is, and this one accurately, that would mean that these two sides are the same, these two sides are the same, and then we'd have our point of concurrency. Alright, so the point of concurrency of the medians of a triangle is called the centroid. So again, centroid comes from medians. It's always inside the triangle, so that's always one of those kind of true or false or sometimes never kind of questions. The centroid is also called the center of gravity because it is a point where a triangular region will balance. That's kind of a little fun fact there. So if I made this triangle out of wood or whatever and then balanced it on some sort of metal tip right there, it would balance. So pretty cool. Good one to know. So this is where it gets a little interesting. The definition, or the perk of having a centroid, is that it's 2/3 of the distance from each vertex. So it's kind of weird to think about, but the idea is that if you took this line and broke it up into 3 equal parts, 2 of them would be from B to P, but from P to Z would be 1/3. Alright, so I like to call it kind of this 2/3, 1/3 idea, but they will give you this formula here. So for instance, if you knew the entire length of AY, if you multiplied it by 2/3, you'd get AP, which is that larger half. If you multiplied it by 1/3, you'd actually get PY, which is that other piece. Alright, so that's the idea of the 2/3, 1/3. And so if we take a look at this one, notice it's saying use the centroid to find the segment lengths. And you can see they're centroids because they go from the vertex to its opposite side, cutting it in 2 equal pieces. And so, if we use what they give us, let's see, RL is 21, so that's this entire length. And SQ is 4. If we are trying to find LS, LS is going to be this 2/3 piece. And so all we would need to do is, I mean, at least the way that I think about it, is I break it up into its thirds. So if this entire thing is 21, then each of the pieces is 7. And then it's a lot easier to identify that LS is just going to be 7 plus 7. But if you want to use the formula, you can say that LS is going to equal 2/3 of RL. And so 2/3 of 21, and so that's 14. But again, I like the visual of it, so I like to break it up into its pieces. This same picture is on the next one, but now they want you to find NQ. So NQ is this middle piece, and then they're saying that SQ is 4. Well, if SQ is only 1/3 of this, that means that up here there's another 4 and another 4. So each of these is broken up into 3 pieces. And so if we want NQ, all we need to do is add NS and SQ, and NS is 8 and SQ is 4, so we have 12. Of course, we could use the other formula to kind of find NQ, but again, I like the visual of this piece. Okay, so these next ones here, rather than being told that it's a centroid, right, in our directions kind of here, we have to determine that it's a centroid, and we know it's a centroid again because we have a vertex to an opposite side that's cut in half. So, they're telling us first that ZW, where's that here, is 7. And then LX is 8.1. Where's LX at? This whole thing here. So if we want to find KW, it turns out that LX is not going to be helpful, so we'll just keep the red piece instead. So ZW is the shorter piece. The shorter piece is always from the centroid to the bisector. So might want to make a point that the shorter piece, or the 1/3 piece, is from centroid to midpoint, versus the longer piece, which is 2/3 of it, is from the centroid to vertex. Just to kind of have that, because sometimes it doesn't necessarily look the same length. So if we take that into account, that's the shorter piece, which means this is broken into 2 equal other pieces of 7. And so to find all of KW, we would just take 7 and add it 3 times and get 21. The other one uses this same setup, only now the entire piece of LX is 8.1, and they are only asking for L to Z. And so remember, that's the longer piece. And so if the entire thing is 8.1, that's where sometimes my method isn't exactly intuitive. It turns out that that 8.1 is actually divisible by 3 2.7 times. So that means that each of these is broken into 2 pieces of 2.7. So we have 2.7 here, 2.7 there, and then also 2.7 here. So 3 2.7s. So if LZ is 2/3 of that, then we just need 2.7 and 2.7, add them together and get 5.4. Alright, moving on. So that was the median, and now we're going to altitudes. And altitudes of a triangle are a lot more interesting or intricate, especially because this one leads to the fact that an altitude can be inside, outside, or on a triangle. So for an idea of that, on a triangle, the altitude, if it's a right triangle, is this piece right here, the altitude. If you have an obtuse triangle, very often an obtuse triangle, let's see, drawn in this manner, will have an altitude that's actually outside, and they end up kind of drawing these dashed lines, and so your altitude is that piece. And then it can also be inside, so if you have something like sorry, I was doing them all in green. If you have something like an isosceles triangle or an acute triangle of some sort, the altitude is always going to be kind of inside this triangle. Notice that all of them are meeting at 90 degrees, so it is a perpendicular segment. And so, especially if you're looking at this one here, it's easiest if you rotate it as you're thinking. So, for instance, if I rotate this a little bit, if I pretend that this triangle is sitting on this base, so here's my triangle, sitting on this base, okay, then our altitude is right here. The line that contains the altitude is this entire thing, because these would meet at 90 degrees. If you rotate and make it so that this is your base, you now have an altitude that's actually right here in the middle of the triangle, again meeting at 90 degrees. And then if you rotate one more time, so that this would be considered the base that it's sitting on, the altitude would be this piece, again meeting at 90 degrees. And then the line containing the altitude is this. Of course, all of those lines, as we've just been talking about, would meet at this point here, which has a name that we'll get to on the next slide. So, basically, altitudes is another name for height. It's just easier to say altitude when it comes to this type of measurement because mostly height you think of vertically, but of course here we are with an altitude that's kind of diagonal. So it just depends on your reference point on what height is, and so therefore we call it altitude. Alright, so then we have all the altitudes, and the altitudes all meet at something called an orthocenter. So, orthocenter. This one here is just describing that QRS, our triangle here, has each of these altitudes. So it's got QY as an altitude, RX as an altitude, and SZ as an altitude. And then they all meet at this point of concurrency, which is the orthocenter. Most of the time this orthocenter is more helpful when we talk about finding the area of a triangle, because you always need the height when the area of a triangle is considered half base times height. So just kind of as a reference point, a lot of times orthocenter will lead to areas of a triangle. So height of a triangle is the length of an altitude, but of course the idea of these altitudes is that they would all continue on and meet. So there is a height, that's a segment, but then there's also the line, which is your altitude. This here is a very helpful chart to kind of summarize what we've been doing. Today we talked about centroid, which comes from medians, and then that whole 1/3, 2/3 reference. We also talked about orthocenter, which comes from altitudes, and it usually leads to areas. And then the previous day, we talked about the circumcenter coming from perpendicular bisectors, and the fact that there's this surrounding circle. And then our incenter, with your angle bisectors, was talking about an inscribed circle and some radii. With this, you also, and we saw it, you may end up having to use the Pythagorean theorem to find missing pieces, just because there happens to be right triangles involved. So anytime that there's a right angle, you may end up having a right triangle, which may be Pythagorean theorem. So this is just a summary page that actually would be, if we were taking standard tests, would be given as part of a formula sheet. So just our formula or reference sheet. Alright, so this one here, we're going to find the, this is talking about that balance point, and so remember that the balance point is actually part of the centroid. Imagining it being an orthocenter would be weird if this was obtuse, because it would be out here, so it's hard to balance on something that doesn't exist on a triangle. So the centroid is always in the triangle, and remember that it connects the center of a line. So this is your center of this line, because it goes up 2 over 1 to kind of get from one end of the segment to the other. And then this is its vertex. So if we connect those, and then maybe another easy one to identify would be the midpoint here, which is kind of up a half over 2, and then its vertical line going straight down here to the vertex, means that our centroid is right here. And so your centroid is going to be at far over 8 and up 5. So if this sculptor makes this kind of on this diagram, they would go to this central point and balance. The next one, they want you to find the orthocenter, so we're going to graph this and then find all of the heights to meet. Remember that in order to find a point, as I just did in this other one, points come from 2 lines. And so as long as they are accurate, you don't need 3 lines in order to find that intersection point. So that's probably what will happen with this one as well. So our first point is over 3 down 2, so that's right here, and that's x. Then we have over 3 up 6, and that's supposed to be our y, and then over 7 up 1. Alright, and so if we connect each of these sides with hopefully much better lines than what I'm making here, let's see, we're finding heights. So one of the heights is not that hard, because it's just going to be straight from this opposite side to the base at 90 degrees, because they would meet at 90 degrees there. And so it's going to be any point that's on that line. That's going to be one of the heights. And of course that line goes on in both directions. Then the other one's going to be kind of difficult. Let's see, we go over 2 up, I don't like fractions, 1, 2, 3, 4, 5, okay, well it's going to be fraction no matter what. So, the other one, a midpoint, especially if you actually count it, rather than my weird wobbly line. This is going to be the center of that line. And then the center of the other line is going to be 2 right here. So neither of them are really all that helpful when it comes to finding a perpendicular line for it. But let's see, what class are we in? We do know how to make a perpendicular line. So let's see, this yellow line has a slope of up 1, 2, 3, so a rise of 3 and a run of 4. And so its perpendicular slope is going to be the opposite reciprocal, so -4/3. We also know that it goes through this point, and so starting from there we can go down 4 over 3 and up 4 over 3. So it's at this point, and we're going to go down 4 over 3. So let's see, down 1, 2, 3, 4 over 3, 1, 2, 3. So right there. And then we're also going to go up 4 over 3. So up 1, 2, 3, 4 over 3 is right there. Oh, it's on a half, kind of. 1, 2, 3, 4. Alright, and so this is the line that would then connect those. We're trying to find where those two lines meet. And since this is on y equals 1, really we would just need to find out how to get a 1 on that line. Oh man, too many exciting points on here. Alright, so I'm going to go back to Algebra 1. In Algebra 1, we remember that a linear line has y equals mx plus b. Let's see, we know that one of the points on our perpendicular line here is going to be at 5, negative a half. And so that means that our x is 5 and our y is negative a half. And then we also know that our slope is negative 4/3. And so to write an equation for this, we'd need to find what the intercept is, which does not look like we can get it by just doing slopes. So, and then our x is 5. So we multiply this out. So that's, what's 20 divided by 3? That's negative 6.6 repeating. And this is negative a half. And so I'm going to add 6.6 repeating, 2.5. Oh, that's negative a half. And so we end up with 6.16 repeating as our b. Going back to the original equation, that means that our equation is y equals negative 4/3 x plus 6.16 repeating. And so if we want to find when it's on the line of y equals 1, we would just put in a 1 for our y and solve backwards. So we need to know when will 1 equal negative 4/3 x plus 6.16 repeating. So we'll subtract 6.16 repeating. And get negative 5.16 repeating. And then we'll divide by this multiplier. And get 3.875. Which is 7/8, 3 7/8. And so that means our point was 1 for the y value and an x of 3 7/8, which I don't know that I would have guessed from the graph. So that means that the orthocenter is at that point. So it's at, 3 7/8 and 1. Now, if we do this one on a test or a quiz or an assignment, you are actually going to have a nice whole number here. So sorry that that one didn't. But it is nice to remember that we do know at least y equals mx plus b. We at least know what a perpendicular slope is. And then sadly there's a bunch of decimals, so it makes it more confusing. So either way, that is our summary of 5.3 medians, which makes an centroid, and altitudes, which make your orthocenter.